So, very welcome to all of you. I hope everybody is fine. And everybody knows that we have been in the framework of perturbation. And we have taken on the basic mathematical method to reach out some of the important results of time-dependent perturbation theory. And today's target is Fermi golden rule, and it's a matter of very short period of time. But at the same time, in order to make this lecture series compatible, make it interesting, I would like to give you another example of the importance of perturbation theory. And a statement is given by a scientist, and the statement is that a flap of a butterfly in Brazil, you know the place Brazil? Is it possible that a swap of a butterfly will create a tornado? You understand the tornado? Will create a tornado in Texas. This was the argument given by a meteorologist. His name was Edward Lorenz in 1960. He was a meteorologist. And 1960, as all of you know, it was probably the beginning of computer age. And this man was simulating the programs. This man was preparing models, the weather models, the weather map. For that, they had to simulate the weather map. And what he does, on one fine morning, he has a data. We have a data, say 2.3147, 2.41322. He wanted to make his calculations very fast. So he thought, let me round off the numbers. I mean, if you have a number, say for example, 6.433217. 217, these are the last values in your number. What is their contribution? Their contribution is very less. Numerically, you don't put those values. So what he did in his simulation, he thought, come on, let me, because the processors used to be weak in those times, so that the computer has not to do a lot of work. What he did, he rounded off the numbers of his data. And when he simulated the problem, the results he obtained, they were massive. The changes he obtained in the new models using those approximations, the course of his weather model changed completely. It showed a completely different result. So what does it mean? It means small changes can bring a massive change in your system. This is why perturbation makes it being an important tool of mathematics, important tool of quantum physics. It's the small change that leads the formation or a destruction of a star. But if we think classically, what do you think? You feel if you want to break something big, what do you think? You think you can break it with a thing which is bigger than that. Isn't it? Yes. This is how we perceive. This is how we feel is right. But Really, the true story is basically small changes. This is the origin of what is known as butterfly effect. You might have heard it. Okay? And this butterfly effect was later on used in chaos theory in quantum mechanics. But it originated from this man. What was his name? Edward Lorenz. He was a materiologist. Okay? So this is how you can understand that how vast this field of perturbation is and what are its pure implications. Now, we have obtained the amplitude, okay? And if I write down the amplitude, an1 of t, okay? What is it? It is 1 by IH cross. Then treating my matrix element to be constant, say M, H, N, and then you have an integral. Okay, it's from 0 to P, and then you have e to the power of I, omega M and T dash dt dash. Right? You remember we had solved it, we calculated it, and what we obtained for this case was A1 of t is 4 m h n by h cross square omega m n square. What was here? Sine square omega m n t by 2. Now this is my amplitude, right? So this equation we have already obtained in our previous classes. Now we want to define the transition probability. Come on, look at the thing. Suppose you have two energy levels, energy level 1, energy level 2. A small perturbation can hit your electron in the ground state. And there is a probability that this electron will make a transition to the higher energy level. Now see, this transition will tell you the story of the atom. It will tell you what atom is. It will tell you about the spectrum that you see in the laboratory. When you check out the spectrum of these atoms. This transition that you have, this is a probabilistic transition. It's not an absolute transition. You have a probability. If you hit an electron with a photon, there is a probability. You calculate that probability using this equation. You want to calculate that probability. What is the probability that this electron will make a transition? It will make a transition to the higher energy state. Getting my point? Now, to calculate this probability, we call this Fermi golden rule. And we define this transition probability. How do we define this transition probability? We define this transition probability. Transition probability. Let me assume a symbol for it. Let me take it T. So what you have two energy levels. You have a photon, and say this is energy EM, and this is energy En. This photon will hit your electron. Now there is a probability that this electron can go to the higher energy level. And there is also a probability that this electron will not go to the next energy level. Are you getting my point? So the probability that it has to go to the next energy level, it's opening a window for you. It's opening the information for you about this system. It's making a big change. It's basically making a resonance. Because the electron must have its own oscillations, the photon must have its own oscillations, and you certainly believe, you certainly mathematically feel that this electron can go to the next energy level only under certain resonance. And all other interactions in which there is no resonance, it may not find itself into the higher energy state. Are you getting it? Okay? So what we have, we define a transition probability. Say I choose a symbol T for it. Okay? Don't confuse this T with time or any other physical quantity or the kinetic energy operator. It's T. Let me choose it as a T. Okay? And how do we define this? So you have, in the real system, you have energy levels. And when you are having energy levels, you have density of states. Right? So density of states is a very mathematical indicator of giving us an understanding of the transition of an electron from one state to another state. So if I assume that rho of En, I will choose M here, is the density of states. What is it? Density of states. Then this transition probability is defined as 1 by T integral minus infinity to infinity A n 1 of T whole square rho of E and dE of n. Right? This is how we write down the transition probability. Okay? And when we calculate this transition probability, it gives us the probability of finding an electron or your system in the next state. So this A n, yeah.
Rho E of M,
Rho E m, okay, because I have used the symbol m, yeah, it has to be E m, okay? And then you have d E m. Now I can use this, I have already written down this. So I can write down the transition probability. Yeah, what will be that? So T is going to be 1 by T integral minus infinity to infinity. Okay? What is A n 1 of T? It is M H n, okay, divide by H cross square omega M n square sine square omega M n T by 2 DEM. Isn't it?
4
Okay, the 4 is, I will use that 4. Okay, here you have a 4. That's it. Okay? Fine? Fine. Okay, now what can I do here? I would like to, assuming that the time of your perturbation is extremely large. If the time of the perturbation is extremely large, this matrix element can be taken out of the integral. Okay? When we do that, what will be T? T will be 1 by T. Okay, can I write M H n divide by H cross square omega M n square integral minus infinity to infinity. Okay, what is left? Sine square omega M n T by 2 divide by omega M n by 2 whole square. I will rather take this omega M n square here. Okay? The 2 that was here in the numerator, I have brought it down because 2 square will give us 4. Right?
Yes.
Okay? Fine. So now, here we have what? DEM. Right? Is it clear?
Yes.
Can I move on? Okay, now think about this DEM. Now, if I think of EM, it is H cross omega MN. Okay? M is the initial state and N is the final state. So EM is H cross omega MN. What about DEM? It is H cross D omega MN. Because you see, my integral is in terms of E here, isn't it? My integral is in terms of EM.
Yes.
But the function incorporating my integral is in terms of omega mn. So I need to change this DEM into omega mn. So for this DEM, what I'll use? Okay, come on. So T will be, okay, matrix M H N by H cross square. That's it. And then you have an integral minus infinity to infinity. Then what you have? You have sine square omega mn t by 2. Then divide by omega mn by 2 whole square times h cross d omega mn. Am I right? Can I do this?
Square W.
Yeah, this is square. Okay. Come on, you're right. Okay, you can see this square and this h cross will cancel. Right? Will it cancel? 1 by t, okay, yes. 1 by t is, okay, this is t, this is the transition probability, and this is whole divided by 1 by t. Is this clear? Fine? Okay. Now what we have here? We have an integral from minus infinity to infinity of something like this, And for that, we have a known integration, minus infinity to infinity. If you have something like sine square x by x square dx, this is simply equal to pi. Okay? This is simply equal to pi. But in your actual integral, what you have? It is omega mn t. Are you getting my point? So when we do that, so this thing, minus infinity, you can do this manipulation yourself. You will incorporate the values. So for this sine square, omega mn t by 2 divide by omega mn by 2 whole square d omega mn. This comes out to be 2 pi t. Okay? So this is an assignment for you. You work on this integral and you can find its value equal to 2 pi t. So this part of your equation has a value 2 pi t. So I can write down the transition probability now. What will be transition probability? That is 1 by t. Then you have m h. This is hp. Okay, you correct it. And because this is the perturbation part. Okay. Then I have missed another important thing in my equations. What was that? It was the density of states. Okay? So at every step you have to incorporate rho of EM. Okay, no problem. I didn't choose to write it because it was causing problem to write down on the board, but I have incorporated it now. Okay? So this is rho E of M, and the result of that integral gives us what? 2 pi t. Now you see this t will cancel with this t. Okay? So what you will get? You will get the transition probability. Where is the h cross? Divided by h cross.
Yes.
H cross is there. Huh?
Yes, sir.
H cross is there.
Yes.
Check it.
Yes.
It's a rate.
Yeah, 1 h cross is there. So what we are getting the final result.
2 pi by
So,
h cross.
so 2 pi by h cross integral m hp n rho of e. Now this gives you the transition probability. You can calculate the transition probability of your system using this equation. And this equation is what is called as Fermi golden rule. Is this clear? Clear?
Yes.
Okay. Now let's choose a problem, okay, and solve this problem. I think I'll give you the problem. Let me not record it now, okay? Let's stop here. You can, I'll give you the problem. Okay, wait for a while. I'll write down the problem here because so I choose a problem in which I introduce a perturbation of V naught cos omega t. This is my perturbation. And what is my aim? My aim is to calculate the transition probability. Okay? When I say the transition probability, you automatically understand you are calculating the Fermi golden rule, right? So you have a problem, and in that problem you introduce a perturbation, and that perturbation is V naught. V naught is a constant, okay? And it has a dependence on your periodic function, cos of omega t. Omega is the angular frequency of the disturbance that you are introducing in your system. So you must have at least understood that how small changes can bring those changes which are which a common intuition will not support. A common intuition will tell you the story of wrestlers. If you have a big wrestler and a small wrestler, you will always feel the bigger one is going to win the job. But that's not the way the nature works. If you rightly remember that Apollo crash, do you remember that? In which a scientist, what was her name? Kalpana Chawla. She was from the same country, and she also died in that crash.
Yes.
And what was the reason of that crash? Was this reason classical in nature? No, the reason was never classical in nature. The reason was purely quantum mechanical in nature. And it was a small perturbation. It was a small perturbation that happened in the spaceship that led to the destruction of that massive rocket ship. And this rocket ship was carrying the most brilliant personalities of the world, including Kalpana Chawla. So this is the point here. So this is the domain that we are looking in the framework of perturbation. So come on, you stop it now, okay? So now I want you to solve this problem. I'm here with you. You try to solve it and see the results.